Good evening, good morning, good afternoon, wherever you are in the world. If you're new here, my name is Stu. Today, I'm going to be going through a live system design of a payments gateway. So typically, you'll get this kind of challenge when you go to a FinTech or something like that, and they will often ask you a very simple kind of question and example. They'll go, design us a payment solution. And typically the payment solution will have two different criteria attached to them. I'm going to show you kind of how you can go through and answer that. So share screen. Let's get our trusty whiteboard. So the two things, hi Rikan, the two things that they are likely going to ask you, the requirements. Nothing special for this stream, so if we get pen to work. Why has this decided not to work today? This is a great start. So if we do this, okay. Give me a second. So the two requirements, as I'm trying to reboot the graphics tablet, the two requirements generally are accept payments, followed by ensuring that. Why is it doing that? Hey, there we go. So our two requirements are one, accept payments. And our second requirement is essentially show it to the user. So typically what I would see when somebody approaches this challenge, they think it's a lot simpler than it usually is. So what they generally end up doing is they have the API there that will do most of their logic. They may have something sitting in the back to process payments. And then that will write to some form of database. It's usually something like SQL Server that they try and write to. And then they might have a UI over here that talks to their API. And if you're lucky, you get some kind of auth server. And this is what I've been on the receiving end of seeing a lot of these architectures. And this is generally pretty much what comes up all the time. Very, very simple. There's not really much for you to talk with the interviewer about and kind of show your knowledge. So people generally try and focus on things like the UI and go, oh, I'm going to be building it with Angular or React or Vue or something like that. And they spend a lot of time kind of going, this is what the user focus is and stuff like this. But all the complexity lives in the API and what's behind it. So if we're looking at like a design like this, we're going to be looking at scalability. Now, depending on which kind of fintech you go for, it depends on your scalability requirements. For example, if you're talking a stock trading kind of fintech, your scalability requirements are going to be a lot higher than if it's just a normal payments processing company. Even some of the, take MasterCard, for example, one of the biggest kind of things in the world, processes 16,000 a second, roughly, on the last time I looked at their data. So if MasterCard, the global worldwide entity, is only processing 16,000, which, to be fair, is a lot of payments a second, then call it 10% that you'll ever need maximum. So we're only talking, call it 1,000 a second, right? Just to be safe. And that would be a very, very large payments company. In reality, you're probably talking a tenth of that. You'll be lucky for most payment companies to hit like 100 a second. Now, it does obviously depend on kind of what you're going to go, what the company does, how they go and do their business. There's a few nuances there, but we're not talking like millions of millions per second for any of the scale. So that's one aspect that we're going to that the interviewer will be looking at is, right, how does the system scale? If they don't explicitly call it out, you can bet your bottom dollar that they're going to ask you during the kind of question process about how to make it scale. Because if they don't put it in the requirements, they love to throw curveballs in like that. So keep that in mind when you're going through the design. The second part is isolation. Isolation is a pretty big deal in payments. How do you keep things isolated? So I'm going to call it isolation and security because they're kind of one of the same thing. So we're talking like, right, where do we have encryption? How do we make sure one person's data doesn't go across to another person's data? And all that kind of stuff. And then the third kind of major thing is, it depends. This one does depend on whether you have kind of payments kind of knowledge going into the interview. But typically, every time I've seen and done a payments gateway test, either me being the candidate or me being the interviewer, there's always been something about fraud. Now, the thing to note here is that when you come up against a fraud process, there is generally a manual step in that process. That could be because an automated system flags a transaction for review, and a human has to look at it and make a risk-based decision to say, yes, I approve this payment to go through, or no, I don't approve this payment. Now, this space is getting a lot better, but this is where AI can come into play as well. And this is another curveball that we'll go into and how to integrate this as well. So with that in mind, let's go through, starting off with our API. I think the kind of front end and auth is, unless the people on the stream want to go through it, I'm going to leave the UI and auth kind of side of things because all the interesting stuff is at the back of it. So we're starting off with our API. One of the first things that we need to do, we can cover refunds as well, killing me. So one of the first things we need to do is talk to the interviewers and get out of them, one, is this an asynchronous system? Or two, is it a synchronous system? Now, generally speaking, payments are asynchronous because of the fraud aspect that I mentioned earlier. So if you're one of the first things that we'll likely want to do when we're accepting the payments for our API is either buffer them somewhere on like a queue-based system, or just somewhere to keep it safe and track the payment. So for example, one approach that we could do is publish it to SNS. Now, this serves two purposes. So as the API request comes in, we do our standard validation with whatever validation logic there is, and we publish it to SNS. That's because we can go into then multiple directions should we want to. One of those directions, assuming we have an SQS queue, may be to write it to a database, which the API talks to. And then the other one for a different SQS queue, maybe your processing one. So this is where it may talk to MasterCard, for example. And then all the updates go back to the database. It's not how I would answer it, but this is just one approach that you could use. So let's take a look at some of the other bits and pieces that I personally would do when taking a look at this. So for the rest of this, I'm going to assume that we're going to be writing an asynchronous system. Okay. Because it's very rarely that you actually need to have asynchronous system in place. And then those words should really be completely different. They sound too similar. So if I was going to design this, the first thing I would want to do is track and store it. And to do this, I would use an actor system. So what is an actor system? Very simply put, an actor system is essentially a container that runs across multiple servers. So if I go out servers down here, that allows you to run instances of objects essentially across all of the servers. And it handles all the communication and all that lovely goodness in between. So most common frameworks in .NET are Akka, Orleans, or Proto-Actor, I think it's called. And they have a very similar concept. The servers underneath are clustered, and then they provide like a mesh-like architecture over the top to basically handle each individual actor. So for me, every time that we come through to the actor system, we're going to write or create a brand new actor. And what this allows us to do is a couple of different things in the background. One, we can do persistence straight off the bat. For example, in the Microsoft Orleans series that I've got on my channel, I show you how to back your actors with something like DynamoDB. So this is a great system here to use. So actor system back to DynamoDB. Why is this a great system to use? Well, clean that up in a second. One of the things that we didn't cover in the earlier part, but is a good bit to kind of show your knowledge and understanding, is we want some kind of notifications to our end users. So we can quite easily develop a system based on something like Lambdas or Kinesis or something like that, coming into our database, coming out the back using the change data capture feeds, and into our notification publishing system, and giving it back to the users. This is a major pattern. If you're going to follow this asynchronous path in your design, this is a major pattern that you want to think about. How do I tell the user whether their payment was successful or not if all I've given them back is like a 201 or a 202, right? If that's the response you're giving them, then you need some way of telling them later. The one thing we want to avoid in our designs is a user constantly going, hey, where's this payment? Hey, where's this payment? Hey, where's this payment? That's going to load up our system, and we don't really want that. We want to say, hey, once we've accepted your payment, we'll tell you in the next, I don't know, call it a minute, that your payment was successful or not. In reality, the payments usually happen in like a couple of seconds, even with all the bells and whistles like fraud and all that kind of stuff. End to end, it's usually no more than a second. So we've got our active system. We've written it to our database. We can also use that change capture feed to run other parts of our system. So one of the other parts that I mentioned earlier was fraud. And you don't really have to explain too much in here. For me, you know, you kind of got two routes. You got an AI route or like a rule-based route. If it's kind of, it depends on like which system you pick as to which approach you kind of go down. The AI route requires a lot of data, a lot of training. So there's potentially going to be some databases around here if you want to go down that route. The rule-based route is going to have some data, but it's all based on kind of data from a third-party data source. So you're going to have like a third party, and more often than not, you have to go and talk to the third party's website or API to say, hey, can you give me the latest rule set for the United Kingdom and the US? Everywhere that I've seen is always based on the United Kingdom and the US rules, even if they operate in other countries, just for jurisdictional purposes. And if you captured like the United States rule sets, for example, it makes your life a lot easier. So if you go down rule-based stuff, expect to be talking to like a third party, but it's these kind of design decisions that you can talk to the interviewer about and say, okay, so if I've got an AI-based system here, then I'm going to have some bigger data sets and all that kind of stuff. You're probably going to have a team that's completely dealing with that aspect of the system. So assuming that we got our fraud part of our system all kind of sorted, the next thing that we're going to want to do with our payment is route it. Because it's highly unlikely that any payments company will have just a single route out of the system. So they're unlikely to have just MasterCard, for example, or just Visa. Usually they'll have both Visa and MasterCard, or JP Morgan and Barclays, HSBC, so on and so forth. And they do this for a few reasons. First one is cost optimization. So if you've got a couple of banks, you can play the banks off of each other with your workload and say, oh, we'll give you more of our throughput and our load if you give us a cheaper bank rate. So routing is a very, very big thing. The other one is failover, because you want your payment systems to be up and running. So we're just going to have a couple of different banks down here, and you need to decide where to send them. So we might just have Bank A and Bank B, for example. One question if you do start drawing this route out is, okay, so how do you manage basically all of these little individual steps? Like we got one here, got one here, and we got one here. And how you manage it is actually a little trickier than what you would think. Because the instinct kind of says, oh, I can just use an SQS queue here. But you can, but it has to be FIFO for the same user. And the reason is, if you send two payments one after the other, it could be in relatively quick succession. We don't know. One could be a big amount, one could be a small amount. So you have to just bear in mind that the order does matter when you're dealing with a payment within the context of one account. So a safer option for this kind of system would be something like Kinesis or Kafka, where you get your high throughput, you get nice partitioning between different accounts and different payments. You get the nice read and write performance out of this, but most importantly, you keep the order as you do so, because they're based on write-ahead logs. Once you've kind of come out the back of the bank, it doesn't really matter too much because you're into a volume then rather than anything else. The payment has already happened, so you just need to make sure it's recorded properly that it has happened. So yeah, just bear in mind that what you put in between each of the systems, ordering generally matters. So after you've done your routing, we need to store it again. So just essentially process results. And that should go back to our actor system there to complete the loop. Now you could argue at every single point, okay, if something happens, we've passed fraud. There should arguably be another path that goes back and tells the system that, hey, I've gone and passed the fraud check. We've done a payment. Okay, cool. Let me go and tell the actor system. We've now processed your payment. So that's all good. So how, I mentioned scalability earlier. How do we scale the system? First part is obviously on your API level. We just run multiple instances of it. And generally speaking, so long as our actor system is up to date, we are good to go. Now how do we scale the actor system? It does depend a little bit on which technology you use, but generally you do exactly the same as you do with the API. You just add more instances of it, and then the actors will self-balance across the cluster, and whichever instance the actor spins up on, it will stay there until it shuts down. And it shuts down usually due to things like memory pressure or stuff like that. But these are only short-lived kind of processes and objects. So hopefully everything's done within a couple of seconds. And soon as you know that you've processed it, there's no reason for you to keep that kind of in the back of the memory, because you've got that notification system to customers. So you can just say, okay, like in, I don't know, 10 seconds after we send the webhook, say goodbye. So question here, that's actually a really good question. So API and actor system, would this be something like Kubernetes cluster or ECS? So I think I said this before on the streams kind of before. Whatever technology you pick, you have to have a great reason for using it, generally. So everything here that I've shown can be run on bare metal, it can run on ECS, or it can run on Kubernetes. There's a lot of times where people think they need Kubernetes and they don't. They're just running simple APIs. They're not using any of the advanced features. They're not really using namespaces or anything like that. They don't need it, but they're putting it in as almost like CV padding. So for me, to keep it simple for the interview, this would all be ECS Fargate. You could equally run it on ECS EC2 if you wanted to, and there would be no problem in that. You would get asked the question, why not Fargate? But to me, the solution doesn't warrant Kubernetes as you're not going to be using any advanced features. You could argue the deployments are a little bit easier with things like Flux and Argo, but generally it's not really needed. So I said, kind of explain the reasons why. So why Fargate? Primarily because I don't have to manage the server. And that is a big win in terms of maintenance. Especially when you work in financial industries and stuff like that, you have to keep your servers and stuff up to date. It's kind of expected by regulators and auditors. And doing that when you've got hundreds and hundreds of instances, yeah, it's a bit of a pain in the ass, if I'm honest. So yeah, Fargate all the way for me. But also just don't overthink the architectures too much. Like if you think, oh, do I need Kubernetes or do I need Kafka? And the answer is probably not. So yeah, just keep it simple for yourself. You save yourself a lot of pain and headaches. So yeah, actor systems. I actually really love them. They work well anytime that you can split payloads. So or anytime you do partitioning and short-lived objects and stuff like that. They're absolutely awesome. And I'll go through like one big feature in a minute that's really helps this kind of architecture out. Notifications, technology that I would be here would probably be Lambda or something akin to Lambda, something that's super scalable, can handle it. Behind, once we get here, we can use something like SQS. We don't need something complicated like Kinesis or Kafka here. We just need to be able to send the notifications. If we do happen to do a retry or they become slightly out of order, it's not the end of the world. So Lambda SQS kind of combination there. And then standard ECS stuff around the back. So this is all very good and well if the system's up and running and we've got some nice queuing features and stuff like that. But how do we keep track of the payment in the system? Obviously, we said earlier that we can have things like notifications coming out and reporting back to the actor system. But let's take an example now. Your routing layer goes down completely. It's gone. How do you know how to track this? Hopefully, we'd have some monitoring and alerting in place. A great default answer, if you want it, for how do we observe systems, you just say it's OpenTelemetry or OTel. You put in the collectors everywhere. You have the collectors and everything writes to the collectors. And then to whatever provider. It's a great standard answer there. But if your payment never come out of routing, how do you know? Because it might have been processed, may have failed silently. And that's a really, really bad thing to happen in a payment system, is a thing to fail silently. So inside of actor systems, they generally have a life cycle. Okay, so if imagine this is our little actor. It has a process called activation. And that's where it reads the state from an external store, like a database. And then it goes into running. And then it deactivates. And this is often where some persistence happens as well. Now, whilst the actor is running, there's a really cool trick that a lot of the actor frameworks have, which is kind of the concept of a reminder. And upon activation, what happens is it says, like, give me a reminder. Just give me a nudge, call this method in 5 minutes, 10 minutes, or something like that, and then execute that code. And if the actor framework is worth its salt, then the reminder will be persisted and it will self-activate as well. So you don't even have to worry about the actor being alive or running in some cases. The actor framework will take care of that and activate the, I'm going to keep calling it a grain because I've used Olean so much, but keep running the actor and basically we can run any user code we want. So we can use this reminder system to build ourselves like a watchdog. And what this is going to do is basically check the internal state and say, hey, I've not seen this payment or an update in the last however many minutes. So this payment should have completed like 5 minutes ago. Why is it not being completed? And you can then rebuild your kind of state and go through and go, oh yeah, no, it got to routing. Okay, let's go and take a look at routing. Oh wait, routing's offline. You can also use it to re-trigger messages and stuff like that as well. So having that kind of timer and reminder system in the actor frameworks is really cool. And that's why we're putting, or one of the reasons why we're putting in the actor system right at the start is so that at the earliest possible point, so in this actor here, first thing we're going to do, persist it. Next thing, set up a reminder. And that so that we can keep track of the payments. After that, return. And if we're using something like DynamoDB, all this secondary stuff like fraud and that kind of comes off the back of it. Obviously, you have to validate your payments and all that kind of stuff throughout here. But that's kind of why we're using the actor system. We persist it, we set up the reminder to do our watchdog, and then job is good. If you have any questions or anything about like why I'm doing something or going down a certain route, please just do let me know. So we mentioned refunds earlier. Refunds can come in a few different shapes and sizes. So refunds can either be triggered by a user or it can be triggered by a bank. So I'm going to need a bit more space up here, actually. Actually, no. I'll just redraw the sections down here. So refunds is just another state in the payment lifecycle. So if you imagine our payment lifecycle is like kind of created, this is very simplistic, but created, sent. Let me see if I can move that safely. Created, sent, processed. And then usually your flow would stop here until you get to the end state of refund. So we'll have to double check against the actor system itself to say like kind of what is the status of the payment? Can we actually process this refund and all that kind of stuff? We may get situations where something comes out of a bank and it just goes straight into our refund process and we kind of have to process it. They may have rejected it for various reasons. Like you got the account wrong and this thing doesn't exist there anymore. The user could also request refunds, and there's a whole, going like too deep into payments, it's a whole way that we can do that. But basically, if it's a user triggered action, it's going to come through our API, either directly through the API or through a UI like a mobile banking app or web app. If it's a bank initiated refund, again, it's going to come from the banks, and then we'll process it in the exact same way. We just change where the source came from. The third way that it can come through, so if that's our customer, we usually have a customer services department. And they can also trigger a refund, which is lovely. So we got like 3 different ways a refund could occur. So we need to have one central place of managing it, because the logic is generally the same, as in check the payment, validate we're in the right state to be able to refund this, figure out where we're going to refund to. In some cases, you may be making a payment back to a card or something like that. So if you're doing, I don't know, a betting company, right? Your user makes a request for your API. They deposit a load of money to you. They then decide they need a refund for whatever reason. You process that refund, but you still got to give them the money back. So you potentially need to go back to your API to re-trigger a new payment. Now, the reason why you trigger a new payment and you don't keep appending states on the end is because you need to capture this whole process again. Is there anything else you wanted to know about, like kind of refunds and stuff like that? Whilst I go clean up some of this. So what kind of curveballs could we be thrown in here? So let's go into this question quickly. So the refund would be applied to the same actor, or is it better to create a new one? For me, it would be a new actor because you're tracking the state in a different way. That said, I would be linking the two payments together. So imagine you have a JSON document and you got your ID of like, I don't know, payment 123. You might also have like a refund ID here. And that might be refund 123. And then you know that you've whether or not you've got a refund associated with that payment. But you still keep all the same benefits of kind of how a refund payment works. In some cases, this is very FinTech, like which FinTech you go into specific. In some cases, you just essentially just give it back to them on their balance. And that's kind of it. Well, that is actually a very good point. And this is kind of a curveball. How do you maintain balances in this system? If you got something asynchronous as this, I'm going to point you over to our lovely actor system again. Because not only can you manage payments in it, you can also manage the accounts in it as well. And this is because, generally speaking, actor systems have a hierarchical nature. So you'll have what's known as a supervisor at the top. And this supervisor is basically a way of keeping track of all of its children. So the root actor will, this is one that you don't generally control, by the way. This is usually a system controlled one. The system controlled actor will look after your actor. Your actor may have children. So the way that we can structure our actor system is take a look at our accounts here. And then you got our payments below it. So when you want to request a payment, you request it through the account. This way you can maintain the balance inside of the account and track the payment underneath. Now, going back to kind of the scalability issue that will always be thrown in somewhere in my experience is, okay, but how does this kind of perform? So I've personally built a system on Microsoft Orleans that every single thing that I was doing to the state, I was persisting the state for durability. And I was getting pretty decent performance. I was getting like 90 a second performance with persistence. Without persistence, it's like 4,000 or 5,000 a second for an individual actor. Given the linear scalability of that as well, excellent performance. And it's very rare, like I said right at the start of the live stream, it's very rare that you're going to have things like a payment system being over a couple of hundred a second. 1,000 to maybe 2,000 kind of worst case, but above that, you'll be fine. And that's total system load. That's not a load on one account. So the most you're going to see on like an account is 3 transactions an hour, 3 or 4 transactions an hour. So there's going to be very lightweight performance in when you split it out like this is not a problem. However, if you didn't have an actor system and you basically trying to use like SQL Server or something like that, and it's all very stringent and fixed, and there's no real partitioning there, then yes, it will be a bit of a performance hit because there's only so many things like SQL Server can do. You're generally talking to a single node rather than a cluster, all that lovely stuff. So that's kind of how you kind of split it out. So you got account 1 over here, account 2, each has a series of payments underneath, and just keeps track of them all. 2 other bits I want to talk about. I'm just going to write them down so I don't forget them. One in a minute, we're going to talk about reporting. And the other one I'm going to talk about first is deduplication. How do you ensure that you only ever process a payment once? That is a very, very tricky thing, if I'm being honest, because as I mentioned, all of the stuff is usually going to be queue-based behind the scenes in some fashion. So you need to ensure that, like for your active system, it's relatively easy, I want to say. But you still have to go through the same process. So you need a way of uniquely identifying that payment. But Tebis, I will come back to that in a second. Alts. So we need a way of figuring out like which is the unique ID. There's no real nice ways of doing that. Best way is kind of content deduplication at the API level. Using some kind of idempotency key that you back with Redis. And then assuming that idempotency key hasn't been used, then you talk to the active system and create it. And once it's been created, then you kind of say, okay, we've completely used that idempotency key now. It can't be used again. And then it puts the onus on the caller to kind of go, okay, I'm going to generate a new one, a new idempotency key. So they might take a hash of the different properties, for example, and then use that as the idempotency key. But generally, that's how I've seen it being done, is API with some kind of idempotency key to Redis into the storage system. Once it's in the storage system, you then have more control over how it gets deduplicated down system. So you might use their idempotency key to generate a unique transaction identifier, which then you can do either content-based deduplication on the transports in between, so the bits in between like the fraud and the reporting and all that kind of stuff, or you can mimic the same Redis setup around the place to essentially deduplicate based on that as well. So you kind of got two options there. When you're working with something in a large volume system and doing large volumes of idempotency keys, you have to figure out how are you going to expire them after a certain amount of time. Otherwise, they're just going to grow at the same rate that all your transactions are going to grow. So if you've been operating for 5 years, you don't want 5 years worth of idempotency keys at a couple of hundred a second to be stored in Redis. That cluster is going to be huge. So you just need to think about how to expire them. That's a business decision, not something you really need to think about for interviews, I wouldn't say. Okay, before I get into reporting, I'm going to take a look at the alternatives to an active-based system. To be honest, if I was going to get rid of it, I would go Lambda based. And this actually would, and the API on the front would be API gateway at that point. the only things that would really change is you just have to go through and do a lot of the things that you would otherwise get for free with things like active systems. So if you think about what we have to do, one, we have to, depending whether it's ingoing or outgoing, check the balance. Two, we need to update the balance potentially. And that would be something we call reservation of funds. And that these first 2 points are only if it's an outgoing payment. Incoming payments you don't have to handle inside of the Lambda functions. 3, storage. So yeah, when you're accepting a payment, you don't need to update like the balance straight away. You can do that in batch later on. So for example, you can wait until you've processed it out the back here from your banks. You could put it into an SQS queue, which is read by a Lambda, and that goes and updates your data store with your payments. And now, instead of processing each individual payment one by one, actually, I wouldn't use SQS there. Go into that in a second. Instead of processing each individual payment one by one, you'd use Lambda's ability to have tumbling windows. So essentially take a time chunk and batch it up and then process batch on batch on batch. This way you're massively reducing the number of writes down on this path and just getting Lambda to do essentially a tumbling window. Sorry, what I'd actually use on this top right-hand side if I was going to go that approach would be something like Kinesis, so that I can partition out, and then the partitions make the tumbling window stuff kind of easy. So I want to answer this one quickly. Lambda has some limitation in terms of memory, and also we don't have issues regarding cold start. Yes, they do. There is a couple of workarounds though. And the last colonial, I haven't forgotten your question, don't worry. So if we're doing like a Lambda response to API gateway, in a system like payments, there's generally predictable flows. Obviously there is bursts when like flash sales and all that kind of stuff comes on, and that is great for like Lambda's scale out abilities. But if you're talking about like general day-to-day payment stuff, it's generally a predictable workload, and there's not much during the middle of the night. It's a whole bunch of stuff as people wake up, dies down on people at work, goes up again at lunchtime, people at work, goes down in the evening, and then kind of hovers it around. So if you know like that kind of pattern, you can say, right, I know that I can pretty much live at that level constantly and the system's going to be okay and functioning. And then you can use things like reserve concurrency and just keep things warm in the background. So if you know what your minimum or your constant minimum is, you can provision them ahead of time. You do pay a little bit more for it, but they're guaranteed to be warm all the time. You'll have a set number of instances that are warm. So that's a great thing. The other thing that people generally forget with Lambdas, cold start generally doesn't matter. I haven't seen many use cases where people are using Lambdas and they really care about latency. Say if it takes 300 milliseconds to spin up in a payment, that's okay. Like it's okay, it's not the fastest in the world, but if it happens like one every, or a few of them happen every couple of hours, I'm not personally that worried about it, so long as I'm meeting my SLAs with the rest of it. And the reason is, you've got to remember what the design is for Lambdas. There's a very, like, they're not designed to be doing loads and loads and loads of business logic. It should be short and sharp, very quick. So things like, I'm just going to write this into the database and worry about it later. Validate the incoming request, store it, send the response back. So if it takes 300 milliseconds to start up every time, I'd be like, not great. But once it's processed the thing, that function stays alive afterwards. Now, it can stay alive for, I think it's up to 15 minutes behind the scenes. Unfortunately, you don't have control over how long it stays alive for. But if you've got a combination of that provision and concurrency, and these Lambda functions are super fast and small, you're going to be fine. The memory limitation, yes, I would generally agree, but I'll go back to what I was saying earlier. They should be short and sharp. So if you're allocating gigs of memory in a Lambda function and you're not cleaning it up, then go and rewrite your Lambda function, basically, because you shouldn't be using that much memory in a Lambda function. Obviously, you can do long-running processes in it, but for a use case like this, I should only be really paying the cost of memory for like whatever it is to store the incoming request into my data store. So yeah, I've gone through kind of like batching, deduplication, securing API gateway. I do want to come back to Last Colonial's question here, because I think this is a very interesting one. Since we talked earlier about one of the requirements being security and isolation. So what do you do to protect yourself in this kind of setup? I'm going to remove our little user for now, so we know what he looks like. So part of the answer does depend on what technology are you using here for your, essentially, your load balancing. So for reference, the load balancing options in AWS, for example, application load balancer, network load balancer, classic, and API gateway. Classic shouldn't be using, so let's get rid of that one. Network load balancer, you don't get any kind of routing capabilities or anything like that, so we can scratch that one off the list. That's just basically port level. If you're familiar with the OSI level, I think it's layer 3 routing that the NLB can do, whereas the ALB can do layer 7, and the API gateway inherently has kind of layer 7 routing capabilities built into it. So fortunately for us, both of these choices here can put in the Web Application Framework or AWS WAF, which is great because we can define a load of rules and we get the built-in rules from AWS. Plus, AWS automatically gives you something called Shield. There's 2 levels of Shield. There is the free version of Shield, which absolutely everyone gets and protects you from things like DDoS attacks and all that kind of stuff. And then you get Shield Advanced, which you get a little bit more stuff into. I'm not too familiar, so I'm not going to go into details I don't know about. But there's basically 2 levels there. That gives you a certain amount of protection. Now, assuming that we're kind of that's pretty standard across the board for every architecture, there should be some sort of web firewall or the WAF. Should be some kind of DDoS protection. If you don't want to use AWS's tech, you've obviously got Cloudflare, you've got Fastly, there's a whole bunch of other ones. So in terms of your API gateway, how do we secure that? Easiest way is have an OAuth server that you talk to. And then your users authenticate with that, get the token back, talk to the server. It does get a little bit more complicated, especially in the banking world in the UK, where we have things like open banking, when there's all fancy different mechanisms that you can do to kind of do authentication. That's generally one approach for general API-ness. Another approach that I've seen, which is very different to this kind of model, is that in the background, you would have either something like private certificate authority or just generally a certificate for a customer. And actually, no, sorry, this is wrong. My bad. It's the other way around. Your customer will have a private and public key pair. Doesn't have to be a certificate, just needs to be public and private keys. Upon registering in the system, they will take this public key and they'll send it to you somehow. Usually during the onboarding process, they'll give you the public key. So every time they make a request, there'll be some sort of user identifier so you know which person it is that's kind of calling a system. But then they'll sign the payload with their private key, and you can verify it with their public key. And that helps ensure something called non-repudiation, which is basically a really fancy way of saying splitting the responsibilities. Like, you knew this was me, and any action you did after that is your kind of fault. It's a very simple way of explaining it. Once you're inside the system, goes back to one of the points earlier around isolation. So this is going to be like your web tier. That would probably be in one AWS account, your fraud system in different AWS account, notifications, again, different refunds because of the use cases with customer services, different, because you might have like a VPN here that people come in and use and access to refunds from there. Banking systems are down the back here. Definitely isolate them. Make sure the access is restricted. So yeah. Hopefully that answers your question of how I'd secure the API gateway. Basically WAF, Shield, combination of OAuth, and depending on the business, I may be using things like HMAC and public-private keys to secure web requests. Infrastructure costs. It's a very good question. It does depend largely on what it is you're using as technology. So for things like the Lambdas that I've got here, Lambdas are very cheap in comparison. So you can run, I worked out a calculation for a project the other day where me running Lambdas was cheaper than me running Fargate instances. I could probably handle the same amount of load, but it was quite an ordered of difference. So I think for a decent sized series of Fargate servers, I think it was like 4 gigs of memory and 4 CPUs or something like that. It's going to cost me a couple of grand to run, whereas I could process like millions and millions of, I think I put it like 5 or 6 million Lambda requests, and it was like, yeah, it's going to cost you $30. I'm like, okay, well, that makes my decision easy for my personal project. But yeah, it does largely depend on what it is that you're using for technologies. And that is a very, very valid thing for you to go through and talk about in your architecture design. And it is something that if you have an architecture process in your business, they will say to you, okay, how much is this all going to cost? You need to go and figure that out. AWS does have a page, for example, that says, put in your different bits and pieces, and it'll give you the generic pricing. There is a trick there, because if you are a large customer of AWS, they do enterprise level agreements, and I believe Azure does enterprise agreements as well. And basically, you get discounts and free credits and stuff like this. For example, I believe, and don't 100% quote me on this, do your own research, but I believe there is a program within AWS that if you get a third party to do an AWS verified third party to do a well-architected review of your system, you can get credits back for that, which is great because you can fund some of your architecture from that. But yeah, it's really hard to kind of go through a cost like this. In reality, if I say a fully loaded system like this, if I was using DynamoDB, this will be a big cost center because of the read and write units. Lambda wouldn't be that much. API Gateway would be reasonable. Depending on your load, for something like this, high load, 5,000 to 6,000 a month. If it's basically not doing anything, then it could be as low as like $50, depending on what you use for your technologies. So yeah, it really does depend on A, how much volume have you got going through your system, B, which technologies are you picking, because some things like Lambda, you don't pay for them if you don't use them, which is great. You do pay for certain things like extra provisioning and stuff, but generally speaking, if you don't use Lambda, you ain't going to pay for it. Same with DynamoDB, you can do exactly the same. So this is one of the big things about DynamoDB. It is fantastic. The way that you can do partitioning of data, change capture streams, point in time recovery, global secondary indexes to reshape your data and stuff like that. Absolutely amazing. But the cost of it, if you're not careful in how you do it, it can be a killer. So you could have a well-optimized system that spends, I don't know, $200 a month on it. But if you don't optimize it right in terms of which strategy you're using, like on demand or provision concurrency, you could equally be like saying 500 write units when you need that for like 1 second of the day. So yeah, it's one of those things that you really pay attention to, things like Dynamo, and go through, right, read versus write units, how do we scale this effectively, and all that kind of stuff. Because you'll talk about how you tackle data sovereignty issues versus replication. Yep. So this is where it gets very, very tricky. There is if you're a single country fintech, like you just operate in the UK, becomes very easy because you just write into your terms and conditions. Generally, you just write into your terms and conditions that we're going to replicate your data to a different region for disaster recovery purposes. But if you're operating in multiple regions, say, for example, you wanted to run in the United States and you had people in the UK, you have to make sure, like, how do you do that? Easiest way of doing it is to create a multi-tenanted kind of system where you physically isolate the traffic. So what do I mean by that? If I had, let's call it api.bang.com, that was my domain. what I would do is I would just go us.api.bank.com, eu.api.bank.com. And then I would replicate within those regions for disaster recovery. But you do have to be careful about what you do. For example, like there is a rule, I believe, in France where you have to encrypt IBANs. I believe it's one of the only countries in the world that you have to encrypt that bit of information. So if you're going to put your data into a French region and you're working with a French regulator, that's something you have to be aware of. Now, having a tenanted system like this generally is not very user-friendly. So this is way beyond what we would actually go through in an interview, I'd suspect, because usually you only have 40 hours, but we're going to go through it anyway. Actually, we'll go for it because it's a very interesting question. So how do I make a nice user experience for global users and keep my data sovereign? The answer is still going to kind of be the same. We have our EU data. We have our US data. And we have, I don't know, let's call it Asia data. And what we want to do is essentially create a mesh on top of it. So we could use something like API Gateway here. And then we'll have a couple of lambdas that are sitting underneath here. We're going to have one which is going to be our authorizer, and that could be dealing with like all your authentication and stuff like that, making sure the user is authenticated. And then we're going to have our proxy, essentially. And again, you could use something like Lambda for scalability here. You can build it into API Gateway itself, I believe. I'm not sure if it works cross-region, but I was playing around with this the other day. From API Gateway, you can call Lambda functions really easily, and other services using proxies. So I'd be looking at using the proxy capability from API Gateway, and based on the authenticated user, I can always route to the correct destination from a single URL. And then things like reporting become a little bit trickier from a business perspective. If you wanted like a single region for like reporting purposes, then potentially you're going to have to look at data anonymization. So removing all the users identifying traits and stuff and just use generic details like where did it go, how much was it, when did it go, stuff like that. There's a whole bunch of legalities around this, so standard answer of go and read the rules and go and ask your legal departments before you implement any of this. But yeah, this is what I'd be looking at doing. We have our API gateway on api.bank.com. And then underneath, we might have, an eu.api.bank.com. And if for whatever reason the global network's unavailable, you can go and target the region individually. Above API gateway, if we're talking a big system like this, I would always put in global accelerator, AWS global accelerator. Well, what character is that? Tell that's been a long day. If you're not familiar with, actually, I'm going to ask you guys, since there's a few of you on, how familiar are you guys with AWS Global Accelerator? Because it does some really cool things, which I can probably explain in this diagram as well. But I just want to know like kind of how deep to go with it. But basically, on a very high level, AWS global accelerator creates you a global network. Okay. And imagine all right, so we're not at all. Okay. We're going to have some fun. People that know networking are probably going to hate me for some of the explanations I give here, but we're going to go through it as best as I can give it to you. So when you set up AWS Global Accelerator, it gives you an IP address. Let's call it 1.2.3.4. In the same way that as if it was a single server. But what happens is if these are Amazon's point of presence around the world, so not only the regions that you can put all the different bits and pieces in, but also their little points of presence for things like CloudFront, they advertise that IP address for you. So we're going to have, I don't know, EU1, EU2, US1, Asia South Pacific 1, right? And all of these data centers are going to advertise 1.2.4. Okay. And the way they can do this is something called Anycast. Oh, it's called Anycast IP addressing. Okay, and basically, depending on where you are in the world, depends on which server you hit. So if I'm a user down in the South Pacific, I'm going to make a request for api.bank.com, and I'm going to get the address 1.2.3.4. And you're going to go, okay, great. Let's go and connect to that. But which one of these do I connect to? And there is something called BGP, or Borderway Gateway Protocol, I think it is. And essentially, oh, yeah, sorry. My bad. And essentially, what happens with Borderway Gateway Protocol is anything inside of a data center. So you imagine you've got your little router sitting in your data center. That's the thing that advertises the IP address. And all the little routers sitting around the world listen to updates from their neighbors to say, I have this set of IP address ranges. So when you go and connect into your router to start resolving the address 1.2.3.4, it's going to go, I've got somebody that knows how to do 1.2.3.4 not too far away from me. And it routes you to the closest possible location. Now, you may be aware of things that have happened to Cloudflare, where, actually no, Facebook had a big incident, I believe it was a year or two ago, where some BGP routing tables got messed up and it took off Facebook for like a long time. And it was quite a big news story. I believe that was down to somebody basically messing up the routing and then they couldn't get back into their own systems. Quite cool to hear about. But basically, we're just creating a global network, and then the routers inside of Amazon advertise that IP address for us to other routers that are nearby, and creates you kind of like a little boundary in between your regions. And depending on where you sit in your boundary, depends on where you go. This means that we jump onto Amazon's network really, really quickly. So we're not going to, if we're over in Asia and our website is in the EU, we don't have to go all the way through the public internet to go and connect to the servers. We can jump on to our local point of presence, essentially, which AWS manages for us with Global Accelerator, jump onto the local points of presence, and then we use AWS's super fast backbone to go and connect through. There is a charge for this. I don't know how much it is off the top of my head, but it's a really great technology. That's one of the benefits you get from it. I'm going to go through. Does that make sense whilst I'm cleaning up the diagram? Basically, the same IP address is advertised across the world, and you connect to the closest version of it, essentially. So the other really, really cool bit about AWS Global Accelerator is you can do health checks with it as well. And the way this works is if you basically start creating endpoint groups and say, yeah, I've got all these endpoints here and it's all good. And I'm just going to take the EU2 one, for example. And inside of here, you might have an application load balancer, okay? And that might have a health check endpoint on it. AWS Global Accelerator can check that endpoint to say, hey, are you healthy? Are you healthy? And when it detects that it's not healthy, it just goes, takes that region offline, and then routes to one of the other available regions. And does this all based on health checks. When that region comes back online again, awesome. Let's go and publish it, like start sending traffic there again. So it doesn't have to be an outage for this to occur. You may want to do like a really big structural change or something and have a bit of planned downtime in there. If you got 2 European regions, you can mark the first one as unhealthy, send all the data across to the one that's healthy, do your maintenance, bring it all back up again. So yeah, that's like 2 of the major benefits of Global Accelerator. One is one IP address kind of everywhere in the world and the performance benefits of it. 2, help region-based health checking, and then you can fall over it. I've not seen many companies use it, if I'm being completely honest, but it's really great. Don't get me wrong, things like Anycast IP addressing and BGP is pretty complex, but it's worth understanding at least a basic level of kind of what's going on there. We didn't really touch on reporting earlier. In the context of an interview, reporting, if you got in the diagram that we drew earlier, you'll have loads of points where you got like things like kinesis streams and stuff like that. If you got all that kind of stuff in place, then you can just take copies off, assuming that you can take copies off. You can't with SQS directly. You have to go through SNS to do that. But things like kinesis, you can just add another subscriber on, take your data off in real time, and go and do it in a completely different way. Yeah, there's a lot of information. I covered more than what I thought I was going to cover, if I'm completely honest. Do you guys have any other questions about anything we've gone through, or any other technologies that you want to know a little bit more about, and why would we use one over another, etc.? And also, if you do have, like, if you want to know other scenarios, I'm planning on doing these live streams around this time every single week. So if you do have someone that kind of going through it, then, like, you got a scenario that you want to go through, please just drop me a message, leave me a comment, and I'm happy to take a look at scenarios and go through anything. PSD2 is actually not that bad. killer one is PCI compliance to me. And one of the reasons why is we're going to have it in the specification 4.1 that's just come out. But basically, one of the things that they're going to be putting in very, very soon is the idea of if a system is connected, then it has to be encrypted. So let's take a look at what that looks like. So if I got an ALB, point-to-point encryption is that line there. So I might have HTTPS here. Generally speaking, people think that, yes, I'm end-to-end encrypted if I have HTTPS. You're not. You might have a series of containers back here behind your ALB running, I don't know, Kubernetes or ECS or whatever. You have a second point here. That also needs to be HTTPS. Fun fact about AWS ALBs is they do not care whether the certificate you use to respond to a HTTPS connection onto the ALB, i.e. going this way, they don't care if it's valid or not. And the reason for that is for things like private certificate authority, it's essentially a self-signed cert. The ALB is no way of saying trust this certificate, so you just don't. So that's another point. Now, where it becomes really interesting from a compliance perspective is if that container was a sidecar, like Envoy. Just take Envoy, for example. The idea of Envoy is basically it creates a service mesh over your containers and you do routing discovery and all that lovely good stuff. And when you've got your container, technically speaking, there is another point-to-point connection there, another system that it travels through. Now, there's a lot of discussions between me and a few others at our previous place whether that constitutes a proper point-to-point connection because it's essentially in process on the same machine. And the conclusion that we came to is play it safe. So that also should be HTTPS. And any databases underneath TLS. You might have a couple of those. So when you're doing everything up to like the load balancer here, it's very, very straightforward. Doing it to an initial container, it's a little bit more difficult because with things like certificate manager inside of AWS, there's only one way of exporting the certificate. You can't actually export the private key unless you've created the certificate through a private certificate authority. So you either upload a certificate and you keep a private key somewhere and load that into your container from, like, I don't know, say you keep it in S3, then you load it in that way. Or you have to use ACM PCA, so Certificate Manager, Private Certificate Authority, and export the certificate from there. And every time you export, there's a little charge for it. Because, you know, cloud, there's always a charge for everything. So yeah, it becomes, when you start dealing with all these point-to-point connections, it starts getting a little funky. With it, when it's managed services on the back end, like if you're using Aurora or RDS or Elasticache or something like that, the background TLS is generally taken care of for you. You just have to enable it in the switches. But yeah, that is all fun and games, which is fine until you have to worry about how do you rotate all of these certificates and how long should you keep them for? Backable view. So this one here from Sleepix. Yes, that is definitely part of it. I did cover this a little bit in the last stream, but since you're here, I'll cover it here for you again now. So if you've got multiple VPCs, AWS, what you can do is set up a third VPC, for example, as an inspection VPC. So your what we call your east-west traffic, so going between networks in your section, goes through this inspection VPC, and inside of there you can put in either a third-party appliance. You can use Network Center to go and do some of that stuff, put whatever tools you want, and you can aggregate all of your logs out there. So you may still have your VPC flow logs coming out of here into a central archive place, but you'll be able to do all your intrusion protection stuff inside of that inspection VPC for the most part. But yeah, it's definitely an interesting one. We used to use alert logic. It's really powerful. I've not heard of alert logic, if I'm honest. When it comes around to kind of intrusion protection systems and stuff like that, at that point, generally an InfoSec team would start taking care of that along with dedicated architects. So myself, I'm not actually a dedicated architect. I'm actually a .NET developer. Primarily, I just happen to know a bit about architecture and DevOps, and I enjoy flowing between the three. Ouch. That is some scale. 2 IDS servers or intrusion detection servers process about 2 petabytes a month. That's quite a bit of data. So yeah, unless you guys have any other questions, I've gone through everything that I've wanted to go through today. So I'm just happy I can stay on as long as you guys have questions or you just want to chat. But if there's nothing else, then I kind of call it quits for today. But I'm happy to answer any questions if you have any about anything. No worries. Thank you very much for staying on. I realize it's been like an hour and a half and you've been here pretty much the whole time. So thank you very much for that. Much appreciated. If you do have any other questions, either that you think of one later on and like something we've talked about here triggers a thought, or you got something else, just feel free to come back, leave me a comment, or hit me up on Twitter at IM5TU. And yeah, I'm more than happy to answer any other questions you have in the future. Otherwise, hopefully I'll see all of you next week. Enjoy. Bye-bye.